This is the analytical report for Experiment 5, Chemical Equilibrium, presented by Justin Noak. The purpose of this lab was to determine how changes in the concentration of reactants and products in a chemical equation affect equilibrium. The lab used Le Chatelier's principles to determine how equilibrium was affected. Le Chatelier's principles explain that when a stress is added to a reaction, the reaction is going to shift to return to equilibrium and alleviate stress. This experiment was broken down into several smaller experiments. The first one being explained is the experiment dealing with acetic acid and the acetate equilibrium. The equation for the equilibrium is shown here. Equilibrium was established by adding 0.1 molar of acetic acid into a test tube, and then the pH of the solution was tested. The first pH measurement was found to be 4. The first pH test was significant because it was the pH of the acetic acid and acetate at equilibrium. This established a baseline pH for the experiment. Solid sodium acetate was added to the solution and increased the pH of the solution to 6. The addition of sodium acetate to the solution is shown here. When the sodium acetate was added to the solution, the system shifted to the left. When sodium acetate dissociates, more acetate ions were in the solution, which increased the concentration of acetate ions on the product side of the reaction, which shifted the system to the left. It is important to note that sodium ions and sodium acetate ions were not included in the equilibrium reaction, so the only substance that changed the way the reaction shifted was the acetate ions. The next experiment being explained is experiment E, which dealt with the iron and iron thiocyanate equilibrium. The net ionic equation for this equilibrium is shown here. Equilibrium was established by mixing 0.1 molar of iron 3 nitrate and potassium thiocyanate and diluting it with water. Then the solution was split into 6 different test tubes. Iron 3 ions were clear and colorless. Also, the thiocyanate ions were clear and colorless. The iron thiocyanate ions were the dark red color. When both the iron ions and the thiocyanate ions were mixed, the solution turned red because the reaction is product favored. So, the reaction shifted to the right towards the iron thiocyanate ions. When heat was added, the color of the solution became lighter, turning a light orange shade. Since the color of the solution became lighter, the reaction shifted towards the left in the presence of heat. Due to the reaction shifting towards reactants in the presence of heat, it can be concluded that the reaction is exothermic. The reaction including heat is shown here. Heat was added to the right or the product side of the equation, therefore it is evident to say that it is an exothermic reaction. When excess of both iron 3 ions and thiocyanate ions are added to the reaction, the system shifted right because more reactants are being added to the reaction. The solution became a darker shade of red when iron 3 ions and thiocyanate ions were added, which proved that the system shifted towards the iron thiocyanate, or the product side. The equations above show the addition of excess iron 3 ions and excess thiocyanate ions, respectively. When silver nitrate was added to the reaction and centrifuged, a white precipitate formed. The Ag ions, also known as the silver ions, formed a complex with the thiocyanate ions, which is what formed the white precipitate. There was a decrease in the thiocyanate ions in the reaction, so the system shifted to the left. The precipitate formed was silver thiocyanate. When sodium hydroxide was added to the reaction and centrifuged, a red-orange precipitate formed. Iron 3 ions formed a complex with hydroxide ions, which formed the red-orange precipitate. There was a decrease in the iron 3 ions in the reaction, so the reaction shifted towards the left. The precipitate formed was iron hydroxide. The next experiment being explained is experiment F, which deals with the bicarbonate and carbon dioxide equilibrium. The equation for this equilibrium is shown here. Equilibrium was established by adding saturated sodium bicarbonate to a flask, as well as 3 drops of bromethymol blue. It is important to note here that bromethymol blue turns the solution blue when the pH of the solution is 7.3 or higher, also known as a basic solution. A solution with bromethymol blue that turns yellow has a pH of 6.3 or lower, which is an acidic solution, and a solution with bromethymol blue that turns green has a pH of 6.3 to 7.3, or a somewhat neutral solution. After bromethymol blue was added, then 6 molar hydrochloric acid was added until the solution turned a greenish yellow color. When the aspirator was connected to the flask, it removed carbon dioxide gas from the flask. When carbon dioxide was removed, the solution shifted right. Since the system shifted right, the solution became more basic, resulting in the color changing to blue. When the bromethymol blue was added to the solution, initially it was blue, meaning the solution had a pH of 7.3 or greater. Then, when the 6 molar hydrochloric acid was added to the solution, it turned a greenish yellow color, meaning the solution had a pH of 6.3 to 7.3. When the aspirator was attached to the flask and carbon dioxide was removed, the solution turned back to blue, making it a basic solution again. Since the system shifted right, the solution turned basic, resulting in the solution being a blue color in the end. Thank you for listening. All the information was cited from the Honors 160 Laboratory Manual.